Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. This is the fifth module of the course. The title of this module is Momentum Transfer of Non-Newtonian Fluids 2. So, there are two modules dedicated for the momentum transfer part. In the previous part, that is the first part of the momentum transfer, we have seen when non-Newtonian fluids such as power law fluids, Bingham plastic fluids and Herschel-Bulkley fluids are flowing through pipes. What are the corresponding velocity profiles and then volumetric flow rate expressions if the flow is laminar, that we have seen, and then for corresponding velocity profiles we have also seen what are the corresponding friction factors. Then again under the turbulent conditions also we have seen what are the velocity profiles for these power law fluids and then their corresponding friction factors under the turbulent conditions, that is the turbulent flow of these power law fluids in circular pipes. So, in this module also we will have three lectures. In three different lectures we will consider three different geometries. This is the first lecture of this module. And in the first module, this first lecture of this module, we are considering flow between two infinite parallel plates. So, we take here power law and then Bingham plastic fluids. So, individually when they are flowing between two infinite parallel plates, what are the corresponding velocity profiles and then volumetric flow rate equations that we are going to develop in this lecture. So, now first consider the power law fluids. Power law fluids flow between two infinite parallel plates, the flow is under laminar conditions. So, this is the upper plate and then this is the bottom plate. The distance between two plates is 2h and then the flow in this pipe is in the z direction, right. So, then flow is laminar, steady, symmetric, incompressible and fully developed flow, that is these plates are infinitely long. So, that you know we do not consider the entry and then exit parts of the plates, we consider the region where the flow is fully developed. Under the fully developed region, what is the velocity profile if the flow is laminar flow, right. So, from the schematic we can see that the flow is in the z direction, and then it is varying in the y direction, that is as the distance between the two plates varies, the flow also will vary. So, the distance between two plates is 2h. So, however, here the flow is symmetric about this plane, about from plus 0 to plus h, whatever the flow is there, the same flow would exist from 0 to minus h. So, then we can solve the flow only in the off domain, right. So, then what we get here, the flow is from the schematic, what we understand, the flow is one dimensional, that is V z, and then it is changing in the y direction. Let us say if the flow, if you draw the profile for the shear thinning fluid, then here you may get something like the flatter profile, and then if it is a Newtonian fluid, then you may get a parabolic profile like this. So, what are these profiles etc., that we are going to see now, and then what we see from this profile, that they are changing, the velocity is changing in the y direction, the Vz velocity is changing in the y direction. So, restrictions the assumptions of this problem is the flow is steady, symmetric, laminar, incompressible and fully developed flow. The gravity is negligible, it is because these plates are horizontal, and then temperature conditions are maintained uniform throughout, that is the isothermal conditions. Now, in order to get the velocity profiles etc., how do we proceed? As in this course, we start with the checking with the continuity equation, whether under these restrictions continuity equation is being satisfied or not, or otherwise are we finding any boundary conditions or limiting conditions from the continuity equation. That is what we are going to see, and then we simplify the momentum equation, so that to get some information about the pressure as well as the shear stress. From there we get the velocity profile subsequently after substituting for the shear stress in terms of the velocity gradient. So, now continuity equation in this Cartesian coordinates is given here, dou rho by dou t plus dou by dou x, rho v x plus dou by dou y, rho v y plus dou by dou z, rho v z, right. So, it is a steady state problem. So, dou rho by dou t is 0, and then v x is not existing, v y is not existing, v z is existing, but Vz is not function of z, that is another one reason. Another reason is the fully developed flow. The flow is in the z direction, so fully developed flow dou by dou z of velocity or shear stress is 0. So, continuity is satisfied here, right. So, then x component of momentum equation if we see, so it is given here. So, from this equation also, for this equation also we try to apply the constraints of the problem, so that we can get some additional information, right. So, it is a steady state problem. So, first term in the LHS is 0 cancelled out, Vx is not existing, Vy is not existing, Vz is existing, but flow is fully developed. So, dou by dou z of velocity terms should be 0 because of the fully developed flow. Pressure we do not know anything about the pressure. So, tau xx would have the terms dou Vx by dou x terms only. So, Vx is not existing. So, this altogether dou by dou x of tau xx will be 0. Tau yx will have velocity components Vy velocity and Vx velocity. So, but both Vx and Vy velocities are not existing here. So, dou by dou y of tau yx will also be 0. Then because of the fully developed flow, this term is also 0, and then there is no gravity in this the flow geometry that we have considered. So, the last term gravity term is also 0. So, what we get from here? We get dou p by dou x is equals to 0. So, what does it mean by p is not function of x? So, what we understand by simplifying this x component of momentum equation by applying the limitations of this problem, that we get this information that pressure is not a function of x, pressure is not varying in the x direction. Next is y component of momentum equation. So, it is given here. So, if we apply the constraints of the problems, assumptions of the problem here also. So, steady state. So, the first term is 0 in the left hand side, Vx is not existing, Vy is not existing, Vz is existing, but because of the fully developed flow, dou by dou z of velocity components here is 0. So, dou p by dou y we do not know anything about that. So, let keep it as it is. Dou by dou x of tau xy will have the terms Vx terms as well as the Vy terms. So, both Vx and Vy terms are 0 here, they are not existing. So, this tau xy will also be 0, and tau yy is having dou Vy by dou y terms. So, Vy here also not existing. So, then this term also will be 0, and because of the fully developed flow condition, this term is also 0, and because of the no gravity, the last term gravity term is also 0. So, here what we get? We get dou p by dou y is equals to 0. So, that indicates that the pressure is also not function of y. So, what we understand from these two equations? So, pressure is not function of x and y. So, this is what we understand now. Now, we go to the z component of momentum equation. So, that is given here. Here also if we apply the boundary if we apply the assumptions, the steady state problem. So, first term in the left hand side is 0, Vx is 0, Vx is not existing, Vy is not existing. So, that is also 0, Vz is existing, but dou by dou z that is fully developed flow, because of fully developed flow, dou by dou z of any velocity component is 0 here. So, that is 0. So, pressure we do not know anything. Tau xz is having the velocity component Vx and Vz, right. Vx is not existing, but Vz is existing, but Vz is not function of x. So, here in the tau xz, Vz would be the function of x. So, the term is 0. Here tau yz, Vy and Vz are existing, and then Vy is 0, and then Vz term is function of y. So, Vz is function of y. So, this term will be there. So, we cannot cancel out. So, because of the fully developed flow, dou by dou z of velocity terms, shear stress terms etc. would be 0. So, the last term this dou by dou z of anything is 0 here. So, last term dou by dou z of tau zz is 0 here. So, the last term is rho gz, that is the gravity term is not existing. So, that is also 0. So, what we get from here? Dou p by dou z is equals to dou tau yz by dou y. So, that is what we get. From this equation we can get the required velocity profile. So, but before proceeding to the velocity profile, what we can see here from this equation, we can see that left hand side is function of z only, because we have already seen that pressure is not function of x and y. So, pressure left hand side would be a function of z only. and then right hand side term dou by dou y is there, and tau y z also dou v z by dou y, only v z velocity is there, and that is function of y only. So, right hand side term is function of y only, left hand side is function of z, right hand side is function of y only. So, what does it mean? Both of them are independent of each other. So, so then what we can say that these two terms we can equate to one constant C1. Let us say dou p by dou z is equals to C1, then we get p is equals to C1z plus C2. Now, that plates two extremes of the plates are z is equals to 0 and z is equals to L. So, if the pressure if the pressure at z is equals to 0 is P naught, so then you substitute this boundary condition here. So, then you get from C2 is equals to P naught. So, other extreme, if that z is equals to L, if P is equals to PL, then if you substitute this boundary condition here, and then in place of C2 if you substitute P naught, you will get C1 as PL minus P naught by L. C1 is equals to PL minus P naught by L. So, if you substitute the C1 and C2 here in this equation, then you get P is equals to PL minus P naught by L z plus P naught. From here what we can get, dou p by dou z is equals to C1, and C1 is equals to PL minus P naught by L. So, this we can write minus delta P by L, we can write minus delta P by L, and then minus delta P is nothing but minus of P naught minus PL. So, now this dou p by dou z is equals to C1, that is equals to minus delta P by L. If you substitute here in this equation here, you get dou by dou y of tau y z is equals to minus delta P by L. So, that is what we get. By substituting that, we get dou by dou y of tau y z is equals to minus delta P by L. Now, if you integrate this equation, you get tau y z is equals to minus delta P by L multiplied by y plus C3. But we know at the center between two plates, that is at y is equals to 0, shear stress is 0. So, when you substitute this boundary condition here in above equation, you will get that constant as C3 as 0, C3 is equals to 0. So, finally, that between these two plates, the shear stress is varying linearly with the y direction. It is varying linearly with the y direction, and then it is given as tau y z is equals to minus delta P by L multiplied by y. Now, until this point there is no effect of the fluid, until this point there is no nature, the nature of the rheology of the fluid is not incorporated up to this point. So, but we need to find out the velocity profile for the power law fluid as well as the Bingham plastic fluid. So, first we take the power law fluid. So, if the power law fluid is existing, so then we have tau y z is equals to m into minus dvz by dy whole power n. Why we have taken minus here? Because between the plates, two plates, the velocity here, velocity decreasing by increasing y. So, then y as increases, the velocity is decreasing. So, this is a 0 velocity, and then at the center it is having some kind of maximum velocity. So, that is the reason we have taken minus dvz by dy. So, now this minus dvz by dy, if you substitute in equation 1 and then simplify, you will get the velocity profile. So, equation 1 is minus delta P by L y is equals to tau y z, and tau y z is nothing but m into minus dvz by dy whole power n. Now, you rearrange this equation such that minus dv is equals to minus delta P by L m whole power 1 by n y power 1 by n dy. When you integrate this equation, you will get minus Vz is equals to minus delta P by L m whole power 1 by n is constant. So, integration of y power 1 by n with respect to dy, we get y power n plus 1 by n divided by n plus 1 by n plus constant. So, this Vz we can write it as minus n by n plus 1 multiplied by minus delta P by L m whole power 1 by n y power n plus 1 by n minus constant, because now minus we have taken into the right hand side. Now, we need a boundary condition to get this constant. So, we know that at the wall, that is at y is equals to h, at the wall, that is y is equals to h, velocity is 0 because of the no slip condition. So, when you substitute Vz is equals to 0 and then y is equals to h in this equation, then you will get constant as minus n by n plus 1 minus delta p by Lm whole power 1 by n h power n plus 1 by n. Now, this constant if you substitute back here and then rearrange this equation, then simplify and rearrange that final V z equation, you will get V z is equals to n by n plus 1 minus delta p by Lm whole power 1 by n h power n plus 1 by n multiplied by 1 minus y by h whole power n plus 1 by n. Now, maximum velocity is at what location? It is at the center between two infinite plates. The center is at y is equals to 0. So, in the velocity expression, if you substitute y is equals to 0, you will get the maximum velocity V z max is equals to n by n plus 1 minus delta p by Lm whole power 1 by n h power n plus 1 by n, right. So, now you got the velocity profile varying with the y direction, and then maximum velocity expressions are you have already got, right. Now, you can obtain the volumetric flow rate, because now already you know the velocity profile. So, q is equals to the volumetric flow rate, q is equals to integral 0 to h v z 2 w dy. W is nothing but the width of the plate in the x direction, and then dy is the in the direction that is the some layer of fluid of thickness dy between two plates, y is equals to minus h and then y is equals to plus h, right. So, we have taken only 0 to h, because this we multiplied by 2, so that it can also take the contribution of the lower portion, and then volumetric flow rate is the complete volumetric flow rate, but not the volumetric flow rate in the off region only. So, it is a complete volumetric flow rate between two plates. So, now here in this equation you substitute V z and then integrate. So, 2 w integral 0 to h n by n plus 1 minus delta p by Lm whole power 1 by n h power n plus 1 by n multiplied by 1 minus y by h whole power n plus 1 by n dy. So, this part is constant, right. So, q is equals to 2 w, that constant is as it is, and then integration of dy is y minus from this part 1 by h power n plus 1 by 1 if I take common. So, you have this y power n plus 1 by n, integration of this one is y power 2 n plus 1 by n divided by 2 n plus 1 by n, and then now you substitute the limits 0 to h for y is equals to 0, and then y is equals to h. If you substitute here, then you will get the volumetric flow rate. So, when you substitute this one, first h, then this 1 by h whole power n plus 1 by n is as it is. Next, this in the denominator 2 n plus 1 by n you can write as n by 2 n plus 1, and then h power 2 n plus 1 by n. So, from this equation whatever 1 by h whole power n plus 1 by n is there, that you can write it as h power minus of n plus 1 by n, right. Then you combine these two terms. So, then you will get this left hand this first term constant is as it is, h minus h power minus n minus 1 plus 2 n plus 1 by n, that is h only. So, this overall it comes out to be h. So, if you take the h common, so then 1 minus n by 2 n plus 1 into h you will get here. So, this is nothing but n plus, when you take the LCM you get n plus 1 by 2 n plus 1, and h is as it is. So, the volumetric flow rate of the power law fluid flowing between two infinite parallel plates is nothing but 2 w h multiplied by n by 2 n plus 1 multiplied by minus delta p by Lm whole power 1 by n h power n plus 1 by n, right. So, what you can do once you have the volumetric flow rate, you can find out the average velocity by using this expression, that is volumetric flow rate divided by the cross section area through which the fluid is flowing. So, that is 2 h w. So, if you divide this equation 5 by 2 h w, you get the average velocity as V average is equals to n by 2 n plus 1 minus delta p by Lm whole power 1 by n h power n plus 1 by n, that is the V average, that is average velocity, right. This is how we can do simplify any geometry and get the required velocity profile and then volumetric flow rate. Okay. So, next what we do, we take the Bingham plastic fluid. So, Bingham plastic fluids, so the geometry is same, the two infinite parallel plates are separated by distance 2h, that is between minus h to plus h. The flow is symmetric. So, then I can take only half domain, that is y is equals to 0 to y h domain, and then do the analysis to get the required answers. But in addition to the previous problem, what is the difference here we have? It is a Bingham plastic fluid. So, we know that this Bingham plastic fluid does not flow until and unless applied shear stress is more than the yield stress, right. And then we already know that shear stress is 0 at the center and then maximum at the wall. So, as you move away from center to the upward, so the shear stress gradually increases, and there will be some kind of point, let us say y is equals to HP point, that is the point where the shear stress becomes equals to the yield stress. So, up to that point the flow, the material flows like a plug, like n mass, like a solid material it flows, it does not deform in this region. Then after crossing this region, this y is equals to HP, that is the point where the shear stress is more than the shear stress is equal. After this point, the shear stress is more than the yield stress. So, then the fluid will start deforming in this region, that is between y is equals to HP to H. In this region deformation would be there, and then the material will flow like a viscous fluid, right. So, that is what we are going to see now. It is so now in place of one velocity profile, you have to develop two velocity profile. One is for the shearing zone where the deformation is taking place, another one is the non-shearing zone where the material is flowing like a solid end mass, like a plug. Okay. The conditions are same, the velocity only Vz component is existing, and then it is function of y. So, the velocity Vz component is only existing and it is function of y, Vx is 0 and then Vy is 0. All other assumptions are also exactly same as in the previous case where we have taken the power law fluids. Here only the change is the fluid is changing, geometry and then other assumptions are not changing. So, this simplification of the continuity equation, x momentum equation simplification, y momentum equation simplification, z momentum equation simplification are quite exactly same like a previous case. So, I am not repeating, right. So, then this getting this pressure distribution is also exactly same. Now, up to this point, up to this equation 1, the nature of the material, that is the rheology of the material has not been incorporated up to point 1. So, then up to equation 1, the solution is exactly same as the previous case of the power law fluids. Now, in place of this tau yz, we have to substitute the corresponding expression for the Bingham plastic fluids, right. For Bingham plastic fluids, we know that tau yz is equals to tau naught b minus mu b dvz by dy. This minus we have taken because here the shear rate is negative in this region between 0 to h, or rather between 0 to h or probably hp to h, because 0 to h now it is a shear between hp to h, because for y is equals to 0 to hp and the shear rate is 0 because Vz is constant, that is the maximum velocity or Vzp, right. We are going to develop this one also, right. So, now we rearrange this equation 1 and then in place of tau, first we substitute this in place of tau yz in equation 1, we write this tau naught b minus mu b dvz by dy and then simplify. So, you will get tau naught b minus mu b dvz by dy is equals to minus delta p by L y. Now, rearrange this equation so that dvz by dy term is one side and then remaining terms are other side. Now, integrate this equation, integration is simple here, this term tau naught b, here you get y and then this y, integration of y you will get y square by 2 plus constant, right. Now, we know that boundary condition, that is at the wall of the infinite plate, the top plate, that is at y is equals to plus h, V z is equals to 0. So, then when you substitute V z is equals to 0 here, and then y is equals to h here, then simplify, then you will get the constant. That constant is minus 1 by mu b tau naught h minus delta p by L h square by 2. Now, this constant you substitute here, and then you will get this V z is equals to, the first term is as it is, in place of constant we get minus 1 by b, minus 1 by mu b, and then tau naught b h minus delta p by L h square by 2, this term. So, now from these two terms what you do, you take this first this minus delta p by L terms, h square by 2 mu b minus delta p by L, if you take common you will get 1 minus y square by h square, and then from these two terms if you take common tau naught b h by mu b, you get then if you take this particular term common, so you get here 1 minus y by h, 1 minus y by h. So, this is the velocity profile in the shearing zone, that is between y is equals to h p to h, that is from the point from the upper point of the plug like motion plug to the wall, in that region this is the velocity profile. Now, what is the velocity? Because the material from y is equals to 0 to h p, it is moving like a plug, it is, though it is moving like a solid en masse, but it is moving. So, what is that velocity? So, it is what is that constant velocity? So, then if you substitute in the velocity equation y is equals to h p, then you will get that V z p, that is the maximum plug velocity, right. So, then that is what we do here, wherever y is there, in place of y square we have written h p square, and then here in place of y we have written h p. So, then what you do, in the second step, in place of tau naught b, what you write, minus delta p by L h p, because we know that tau naught because we know that tau y z is equals to minus delta p by L y, and then tau naught b is nothing but tau y z at y is equals to h p. So, it is minus delta p by L h p. So, in place of tau naught b, if you write here minus delta p by L h p, then you get this second step. Now, from this step what you do, you take common h square by 2 mu b minus delta p by L, remaining terms are inside the parenthesis as it is. You simplify these terms, you get here 1 plus h e by h whole square minus 2 h b by h, that is nothing but 1 minus h p by h whole square. So, h p by h is nothing but tau naught b by tau, that is nothing but, let us define as pi. So, then V z p is equals to h square by 2 mu b minus delta p by L multiplied by 1 minus pi square. This is the V z p, this is also the maximum velocity, and this is valid for the non-shearing zone, that is the material which is flowing like a plug, like a solid plug. So, that is between y is equals to 0 to h p. Now, you have the velocity profile for the solid en masse like plug motion as well as the shearing zone. So, that means that the entire velocity profile you are having it, right. So, now what you can do, you can obtain the volumetric flow rate. So, volumetric flow rate here is q integral V z 2 w dy integration 0 to h, lower and upper limit of the integration is 0 and h. So, but now this V z is having two components, one is the plug velocity 0 to h p between y is equals to 0 to h p, and then shearing velocity between shearing velocity V z between y is equals to h p to h. So, V z and then V z p already we have derived. So, let us substitute them here. Here in place of V z p, if you substitute this particular term and then integrate it, you will get integral of dy is nothing but y. In the second, in here if you substitute V z and then do the integration of this part with respect to y is y minus y cube by 3, and then that h square is as it is, substitute limit h p to h. then integration of this part 1 minus y by h, because the other parts are constant. So, you have y minus y square by 2 and then h is as it is, right. And then further in this step, here again tau naught b we have substituted as minus delta p by L h p. Now, what we do? We substitute the limits. So, first here y 0 to h p. So, we have the h p. Here in the second term, first h we have to substitute. So, h minus h cube by 3 h square. Next h p we have to substitute. So, minus h p plus h cube by h p cube by 3 h square. Here also we have to substitute the limits h p to h. First h. So, h minus h square by 2 h minus h p plus h p square by 2 h. Now, what we do from this all these terms, what we take common, 2 w is anyway that is common for both of these terms, all terms. So, then 2 w in addition to this one h square by mu b minus delta p by L, and then h we take common. So, here what are the things are remaining? 1 minus pi whole square by 2, h p is there, since h also taken common. So, 1 h p by h will come. Similarly, all other terms are like this, right. So, when you simplify these equations further by writing h p by h is equals to pi, because pi is nothing but h p by h or tau naught b divided by tau all. So, when you substitute this one h p by in place of h p by h, if you substitute pi and then simplify, then you get here. Now, this term from next step, after this step what you do? You take 1 by 3 also common, take 1 by 3 also common. So, here in this first term you will get 3 into 1 minus pi whole square pi by 2, and then remaining terms are like this, right. So, remaining terms are like this. So, what you do next step after this step, you take this particular thing in the front here as it is, okay, and then this particular term without changing you keep it here, right. Now, in the last term what you do? You take 3 pi by 2 minus 3 pi by 2 common. So, if you take minus 3 pi by 2 common from this thing, these terms, if you take minus 3 pi by 2, you will get inside 1 plus 2 pi, so 1 minus 2 pi. If you take minus 3 pi by 2 common, here you get 1, then minus, because minus you have taken common, minus 2 pi plus pi square would be there, right. So, that means 1 minus 2 pi plus pi square I can write as 1 minus pi whole square. So, minus 3 by 2 pi as it is 1 minus pi whole square. So, this term would get cancelled. So, finally, you will get q is equals to 2 w h square by 3 mu b minus delta p by L h multiplied by 1 minus 3 pi by 2 plus pi cube by 2 minus delta p by L h multiplied by h, this is also nothing but tau w, minus delta p by L multiplied by h is nothing but wall shear stress. So, this is how now this is how we can get the velocity profile and volumetric flow rate expression for any geometry, for any type of non-Newtonian fluids, if the flow is laminar and then one dimensional steady flow. So, this is how we have to do, but it is not advised to memorize any of these solutions, final answers, because there are n number of problems with small deviation. Let us say these plates, if you keep it inclined, so the problem solution would entirely change, how it will change, and then all that it incorporating in a final solution in the last step is very difficult. So, it is not advised to memorize any of these velocity profiles or volumetric flow rates, but however the students are advised to go through the steps, how to simplify the momentum equations, and then from the simplified the momentum equations, how to get the velocity profile, and then from the velocity profile how to get the volumetric flow rate, and then once also how to get the friction factors from the velocity profile, how we are doing that steps one has to be careful, and then can get the solution for any problem. So, it is not advised to memorize any of these velocity profiles or volumetric profiles. Even if you are solving some problems in exams, if a numeric problem. So, then these things will be given, or you may be deriving these things and then substituting the numeric values to get the final answer in numerics. Okay. So, this lecture is over here. So, the material presented here in this lecture are mostly taken from this book Non-Newtonian Flow and Applied Rheology by Chabra and Richardson. Thank you.